So one of the last things that we talked about before spring break, we were talking about graphing non-linear functions. We even went through the list of all of the major parent functions that we had, right? And so let's just kind of remind everybody what those were. Okay, so let me adjust this. There we go. So the key guys that we had were the linear function. And I'm just going to do some quick sketches here, and then we're going to go through, review how we do all of the graphs, how we do the shifting, the translations, stretching, compressing, and all that stuff. So your linear function is just that. It's a line, that's it, nothing else. And then we talked about the squaring function. And the squaring function was given by x squared. And the squaring function is a parabola. So we talked about how it's that U shape. We talked about the key points for the parabola. Okay, so it looks something kind of like that. Again, these are just rough sketches. We're going to work on our accuracy here in just a moment. After the squaring function, we talked about the cubing function. Okay, so the cubing function is x to the third, and he is that cactus guy, as we like to say. He gets really steep on the ends right here, but they go in opposite directions. So we call him a cactus because it kind of looks like this. And then we did the square root. And the square root function starts right here at the origin, and he's the half sideways parabola, like that. He does not curve back down. There's no mirroring to this, because if you did copy it down here, it would fail the vertical line test. It wouldn't be a function, and so we couldn't use that function notation. And then something akin to the square root function was the cube root function. And the cube root function looks kind of similar to the square root function, but it's really much more closely aligned with the cube root function, or with the cubing function, because they're inverses of each other. So you have this shape right here, and if you took that guy and rotated it 180 degrees, you would have the other half of the graph like that. So that's what the cube root function looks like. And then the last guy, the nice guy that we had, is the absolute value of x. And the absolute value of x, as you guys remember, is a V shape. And really, he is a piecewise defined function. And he's made up of two linear pieces. You see right here that he is negative x, and then it becomes positive x once you get beyond 0. But that's really a discussion for another time. So these are all the basic shapes that we have. And when we did these guys in class, we talked about what the domains were, what the ranges were. I'm going to kind of skip that for the most part right now. And what we want to focus on is, how do we graph these shapes? How do we graph without having to go to a t-table every single time? You could go to a t-table, but it's going to be wasting a lot of time. Okay, so we have some neat methods, some neat graphing techniques that work not just for these guys, but for any of the basic graphs that you may come across. Because right now we just have those 6 graphs for our parent functions. Once we come back, I guess next week on Monday, in the following weeks after that, we're going to be learning new shapes, and the graphing techniques that we're going to be talking about today are still going to be used on these new looking guys. And if I can, I'll try to show you some of the things on Desmos, if I can get the streaming stuff to work out right for us. Okay. So here's what we need to understand, is that if you have a function, just like in its bare form, and you have something that's added on the outside of this, so f of x plus k, this is what we consider to be outside the function. It's outside the influence of the main pieces of a function, so outside of the radical, outside of the square, outside of the absolute value. When you have pieces like that, as we were saying, outside the function, that corresponds to a vertical shift. So when you see that number, that's going to tell you how to move up or down. Of course, if it's positive, you're going to move the shape up. If it's negative, you're going to move the shape down. For example, if we take the absolute value of x plus 3, well, from the shapes that we talked about on the other page, right? The absolute value is a v-shape, so we know that right away. We know that we're dealing with a v-shape. And what does the plus 3 do? Well, according to what we set up here, it's going to be a vertical shift. And we're going to do exactly what we see. I see a plus 3, so that means vertically go up 3. So this means you're going to go up 3 units. So to get a sense of what this looks like, and again, this is just a rough sketch, it says you're going to march up 1, 2, 3, and here is where you're going to graph your function. You're going to graph the absolute value shape just by shifting up 3 units. Okay. You're not going to change how this opens or closes. All you're doing is that you're taking that shape and you slide it up 3 units. That's all. Compare that to this. If I say f of x is equal to the square root of x minus 5. The audio sounds distorted. Alright, let me see if I can figure out anything that's going on here. I don't really know what to tell you. If it's consistently going on, I really have no idea. I do know that my neighbor's dogs are barking, and I don't know if that's causing an issue. I've been using the same setup that I've been using for the past week or so. It may just be the streaming stuff. Okay, I'm very sorry about that. I have to make sure I check everything else to make sure that I am intelligible. Alright, so for this function right here, we have the square root of x, so we know what shape that is. That's that half sideways parabola that looks like this. And the minus 5 means that I'm going to be going down 5 units. Okay, so let's see what that guy looks like. So normally, just to make sure we understand what we're dealing with here, normally we would have had this shape right here. But now we're going to take that shape and we're going to go down 5 units. 1, 2, 3, 4, 5. So that key point that was at the origin got shifted down 5 units, and then you would just graph from there. All right, let me see something real quick here. All right. Well, I think the microphone is still the same as it has been, so I really don't know what's going on. I'm very sorry about that. I wish things would work out the way I wanted them to work. All right. Okay, well, I don't know what I did, but I'm glad it seemed to work for you. All right, so that's when you have some kind of adjustment that's outside of your function. But then we run into the issue where we have an adjustment made inside. So something that's going to be inside your grouping symbols, inside the square, inside the radical, inside the absolute values, whatever. When you have that, and here, this is considered to be inside the function, then that is going to mean that you have a horizontal shift. Okay, so whatever you see inside your function, that's going to tell you how you move left or right. Now, whatever number you see, you end up doing the opposite of that. We saw that happen with circles before, and we're going to see that happen with a lot of things coming up starting next week too. So, for example, if I ask you to graph a function, and I say x plus 3 quantity squared. The big thing you need to understand about this function is that you have a square. The square tells you the shape. That means that this guy is based off of the squaring function, so he's going to be the parabola. Okay? Having the plus 3 inside means a horizontal shift. But notice how the form is set up for us. In the form, there's a minus. And since there's a minus there, anytime we see this in a form, that means we're going to end up doing the opposite of what we see in order to identify this value that comes after it. So in order to find the h value here, we do the opposite of what we see. So that means that for this guy, I see plus 3, but I'm actually going to be moving my entire graph to the left 3 units. Okay, so we're going to take that parabola and we're going to shift 1, 2, 3 units to the left. And we're just going to graph our parabola from here. And that's really all we have to do. So as long as we know our key points, we can actually build them from this new guy. We can pretend that this is going to be our origin. And with the squaring function, for example, 0 squared is 0. 1 squared would be up 1, 2 squared is up 4, and so on. And so you just build from there instead of having to do a brand new t-table, instead of actually plugging numbers in and having to do the work. All right, if I say g of x is equal to x minus 2 to the third power, the big overriding shape here is going to be defined or determined by the power. So we're dealing with something that's to the third, which means we have that cactus shape, the guy that's going to look like this. Okay, he goes up, he flattens out a little bit, and then he keeps on going up. It's the cubic shape. And inside I see minus 2, so that means I'm going to do the opposite of that horizontally, which means I'm going to go to the right 2 units. All right, so a quick sketch of this. We're going to the right 2, and from here, this is my new origin, so to speak, and I'm going to have this cubic shape right there. So there you have it. Those are the basic concepts for what we're doing here for most of the graphing. Not for everything, but for most of it. And all of this stuff can be summed up in a neat little acronym, okay? And we say IHOD over. Now, I did not come up with this. Had a student share this with me about a decade ago, and I went, oh, that's pretty cool. So here's what IHOD over means. This means that when you have something that is inside your function, that is going to affect you in a horizontal way. You're going to do the opposite of what you see. And if you are shifting left and right, that can naturally have an effect on your domain. Over is going to be very much connected to what you have here. So instead of inside, we're talking about any adjustments that we make outside of the function is going to affect you in a vertical way. You're going to do exactly what you see. And of course, if you are changing things vertically, there is that big potential for you to change your range. Now, if your function itself was already going to have a range of all real numbers, moving all real numbers up or down is still going to be all real numbers. Okay. So let's take this information and start combining things as we look at our graphs. All right, so let's do this. Let's say f of x is equal to the absolute value of x plus 2 minus 5. The big thing we need to see here is that, first of all, because of the absolute values, that tells us our shape. Absolute values indicate that we have a V shape. And we just need to figure out where is that V shape located. Where is this vertex going to be? Where do I start building my graph? And that's where I look to what's inside and outside my function. Inside here, I see a plus 2. But remember, if it's inside, that's a horizontal shift opposite of what you see. So even though I see plus 2, that actually means that I'm going to go to the left 2 units. And then I have a minus 5 on the outside. And when you're outside, this is the over part. Outside is a vertical shift, and you're going to do exactly what you see. So I see negative 5, which means I'm going to go down 5 units. All right, so we have a V shape. We're going to go to the left 2. We're going to go down 5, and that's where it goes. This is just like you grabbing an image on your computer or your phone. You do a long press, and you just move it around. You swipe it around. You're not changing what it looks like. You're just changing its position. That's all. So it's like me, here's that mouse, right? If I move this over, up or down, it's still the same thing. I didn't change the way that it looked. All I did was change its position, and that's what we're doing here with these graphs. So we are going, let's do it this way. From here, we're going to go to the left 2 and down 5. So this is going to be my new origin. I'm just going to mark that. I'm going to use a different colored pen and dash through to create a new x-axis and a new y-axis. Now, if I could, I would just ignore and erase the old x and y axis because I don't really need them. Okay? I only need them to create my new reference point, which is left 2, down 5. From here, we're going to graph our absolute value shape. So you can pretend that this is 0, this is 1, 2, and so on. And those key points for the absolute value were just like graphing a line. Absolute value of 0 is 0. The absolute value of 1 is 1. Of 2 is 2. And you get 3, and so on. So whenever you graph, you want to make sure that you graph all the way to the edge of your graphing window. And on the other side of the absolute value, this guy bounces and it goes the other direction. We need to make sure that we remember that there is a line of symmetry that goes through that vertex. And then, because we are dealing with an absolute value, we have straight pieces here, so I can use my straight edge. And I can't use this for anything else other than a line. Because if you look at the parabola, the cubing function, those guys are not linear. They don't have any linear components to them. So I actually have to graph those very carefully by hand. So here we go. I didn't have to create a new t-table of values. I took my shape and I just shifted it. That's all we have to worry about doing. All right. To another example. Let's take g of x is equal to Let's say this. X minus 4 quantity squared minus 2. Let's try to figure out everything that we know about this function before we actually go to the graph. First of all, we have the shape. The shape is determined by the power. We have a power of 2, so we know that we are dealing with a parabola. And now we just have to figure out what we're doing with the parabola. Well, on the inside here, we see a minus 4. Now remember, if it's on the inside, it's a horizontal shift opposite of what we do. So even though I see the minus 4, I'm going to do the opposite, which is to the right 4. And then the minus 2 that I see on the outside, I do exactly what I see. So outside, a vertical shift, exactly what you see. I see negative 2. And so that means I'm going to go down 2 units. So take the parabola. We're going to go to the right 4, go down 2. So this is going to be my new origin. And we're going to dash a new set of x and y axes through this. And we're going to build our points because this is going to be 0, 1, 2, 3, and so on. So think about what we're talking about here. This is the squaring function. 0 squared is 0. Okay, that's your new vertex. 1 squared is 1. And when we're counting these guys, we were counting from that new x-axis. Don't count from this point. Count from the dashed line. 2 squared, because we're talking about the squaring function. 2 squared is 4. 3 squared is going to be 9, so this is 4, 5, 6, 7, 8, 9. To get other points, we can copy these guys on the other side of the axis of symmetry. So we can copy this one. This one is negative 2 squared is 4. Negative 3 squared is 9. Like that. And we're just going to connect the dots. Make sure that you draw a nice, smooth curve going through these points. You cannot use a straight edge here because this guy is curved. And there we go. So this is what I'm expecting you guys to do on your test. I'm expecting you to plot nice points, clearly define points like this, and draw a nice, smooth curve through it all. All right. Let's keep on going. I mean, I printed off plenty of extra graphs for us, so just don't stop till you get enough. If I say that f of x is equal to the cube root of x plus 1 plus 5. I'm going to give you guys a moment to do that. I need to step away real quick. All right, sorry about that. So hopefully we have already identified the shape. Being a cube root, we know that he's going to have the shape that is like the sideways cubing function. A lot of times students refer to this as a snake. Whatever. If that works for you, great. Now on the inside, we have a +1. And remember, when it's on the inside, we do the opposite. So that means we're going to go to the left 1 unit. And then the +5 means that we're going to go up 5. All right. So again, let's make sure that we put our new origin in the right spot by doing the shifts indicated here. Then we're going to go to the left 1 and up 5. So left 1. So our new y-axis is going to be here because we moved to the left 1. And then up 5. So if you were taking a test, and especially if you were doing any of the homework and it happened to be multiple choice, this should be a no-brainer. You know that's going to be that weird snake-like guy that's going to be going through here, where you have this key point at the origin. And for all of these parent functions that we were looking at the beginning of today's review, they all have the origin as a key point. The functions that you're going to be seeing in the second half of the class, we base things off of the origin, but a lot of the functions don't even touch the origin. They're just a little bit off. All right, so let's talk about the cube root function. Remember those key values that we would plug in. Okay, 0 is always good, 1 is good, but the next number you'd want to have inside of a cube root would be the next perfect cube, which is 8. So 2, 3, 4, 5, 6, 7, and here is 8. On the other side, you'd want to plug in -1 and -8. Know those key values. So the cube root of 1 is 1, and the cube root of 8 is 2. On the other side, the cube root of -1 is -1, and the cube root of -8 is -2. This doesn't have line symmetry like what we saw for these previous two examples. You had the absolute value shape, and you had the squaring shape. Those guys had line symmetry, so what you did on one side, you could copy on the other side. This has what we call point symmetry. What you have going up and to the right is copied with the same kind of pattern going down and to the left. Now, for the cube root function, it's vertical right here instantaneously, and it's going to go up and curve out very sharply to the right, and it's going to go down before it curves out to the left, like that. Okay. What you want to make sure that you avoid is in these 3 points right here, do not go straight through there. It's vertical before it curves out to these pieces. Okay. And there you have it. The cube root is not necessarily my favorite one to graph, but I mean, take your time, and you're going to be okay with it. All right, now let me remind you of a few other pieces of information that we saw when it came to graphing. And this is going to be when we have something that is connected to the function through multiplication, like this, okay? And we know that if a is a negative value, then we reflect the shape across the x-axis. Okay. If a is something that's negative, then it's going to take whatever shape we're dealing with, and it's going to take it and turn it upside down. It's going to flip it over the x-axis. So that means if you had a negative in front of the absolute value, it's going to turn it from being this to being upside down. All of the other shifts that we talked about would still be there. So if you moved left 2 and up 5, you would still go left 2, up 5, but now you would go upside down. That's it. Nothing really tremendous about that. But if the absolute value of that A is something that is greater than 1, okay, then we have a vertical stretch. That's us taking some kind of image, grabbing those bars, those handles at the tops and bottoms, and stretching it out. That's what having a value of A that's greater than 1, at least in terms of absolute value, is going to do. You stretch it out vertically. Now, it gives the appearance of being skinnier, but you have to make sure you understand that the perspective that we're taking is how is it changing us vertically? It's stretching us out. We're not talking about what it does left and right. Vertically, it's going to stretch you out. And on the other side of this, if the absolute value of that scalar multiple in front is less than 1, then we have a vertical compression. So in this case, you'd be taking your graph, and instead of stretching it out, you're going to be squeezing it in, which is going to give the appearance of being wider. But again, we don't want to think about it in terms of a horizontal change. It's how it's changing vertically. So it's compressing it. And the reason it looks compressed is because it's going to be affecting your growth rate. So if you have a 1/2 in front of something, it's only going to be half as high for all those points that we have for those key points for our parent functions. For example, if I ask you to graph f of x is equal to negative the square root of x plus 3. So the main thing here is that we're talking about the square root of x. And we need to make sure we understand that his shape is that half sideways parabola, like that. What does the rest of this mean? So there's nothing inside here that's going to tell us to shift left or right, but there is this negative. And this negative means that you're going to reflect. You're going to reflect this shape across the x-axis. In other words, you're going to turn it upside down. And the plus 3 that's here on the end means you're going to go up 3. So we didn't move left or right, but we are going to go up 3. So it's going to look something like this for our new x and y axes. This being your key point, that being your origin, right? So this is going to be 0, 1. Now remember, for the square root, we want to look at perfect squares. So 1, 2, 3, 4, and then 9 is going to be over here. So the square root of 0 is 0. The square root of 1, now understand this. The square root of 1 is 1. But since you have a negative here, it's going to turn it upside down, so now it's going to be down 1. The square root of 4 is 2, but now it's going to be down 2. And the square root of 9 is 3, but now it's going to be down 3, again, because of the negative. So when you connect these dots, you'll see that we have that same square root shape that we had before, except now it's upside down. We didn't do anything to those points. All we did was turn the orientation of the graph to be upside down. I hope that makes sense. I think for most students, they're okay with knowing that you have to shift up, down, left, and right. But it comes down to knowing what points you're supposed to plot. And so if you forget, you can take something like the square root and do a t-table. Think about what those numbers are that you would want to plug into the square root. 0 is good, 1 is good, 2 is not good because the square root of 2 is not a nice number. That's why we went to 4, and then we skipped to 9, because those are the nice input values that we'd want to look at for the square root function. Now, let's look at this. If I say f of x is equal to 2/3 times the absolute value of x minus 3 minus 7. So there's a lot to unpack in this problem. First things first, though, is that we need to make sure we understand what the shape is. The absolute values here tell me that I'm dealing with a V shape, like this. And what am I doing with that V shape? All right, so with that V shape, I see that inside I have a minus 3. And that tells me that I need to do the opposite. So I'm going to go to the right 3. And then I have the minus 7, which tells me since it's on the outside, I do exactly what I see. I'm going to go down 7 units. The last thing that we need to discuss is this 2/3. Now, having a 2/3 in front, since it's not a 1, is either going to stretch us vertically or it's going to compress us. And it all comes down to how big is that number in terms of absolute value. Is it bigger or smaller than 1? Well, clearly 2/3 being a proper fraction is smaller than 1. So this means that I'm going to end up with a vertical compression. Not by much, but when we compare the final shape of this to the original shape, you're going to see that there is a very slight compression. So we're taking our absolute value shape. We're going to go to the right 3, down 7, and that 2/3 is going to compress it and make these guys less steep. So you're just squeezing those guys together just a little bit. All right, so to the right 3. So that's going to be my new y-axis. Down 7. And there is my new origin. So that's going to be the vertex for my absolute value shape. When it comes to absolute values, these are some of the easiest guys to graph when there is an adjustment in front, like a 2/3, because we can use that 2/3 just like a slope. And the reason we can use it just as we would use a slope is because absolute value functions have straight components. You couldn't do that for a parabola because it's curved, but for absolute value, sure. So start here and go up to over 3, up to over 3. And there you go. To get points on the other side, you want to go up to the left 3. Because if you remember, when we were dealing with those absolute value shapes, we talked about how there is a line of symmetry, which is going to be this guy that's going through the vertex. So you're going up 2 and out 3, up 2, out 3, and so on and so on. And just to make things a little bit neater, let's connect the dots. And these guys are both their own individual linear pieces. And there we go. So make sure that you remember whenever you're graphing for me, you graph all the way from edge to edge of the graphing window, and you put arrows on the ends. Now, you don't always put arrows on both ends because if you look at the last example that we did, this square root shape only had an arrow on the end where he's going off the grid. Here, that's where he starts, so there's not an arrow. There's just a solid point before he graphs out. All right, so that's an absolute value with a compression. Let's do a square root with a stretch. So I'm going to say g of x is equal to 3 times the square root of x plus 5 minus 3. Now you want to make sure that you are very careful in how you write this. Notice that I have 3 in front and it's connected through multiplication. Don't let that 3 sneak into the index nook, where it would then be read as a cube root function. So this is square root times 3. So let's see what we have here. The shape we mentioned not that long ago is that guy. Inside the function we see plus 5. And since it's on the inside, the opposite of plus 5 means we go to the left 5 units, right? IHOD over IHOD. Inside your function, a horizontal shift opposite of what I see. I see plus 5. I need to think negative 5, which means go to the left. And then I have minus 3 on the outside here. So that's over. Outside, vertical shift, do exactly what you see. I see negative 3, so that means I'm going to go down 3. But then we got to pay attention to this coefficient right here. Now that is a positive, so the orientation is still going to be looking like this. But it's a 3, so that means we have a vertical stretch by a factor of 3. Whoop. Vertical stretch by a factor of 3. So here's what I want us to do. I want us to see what it would look like without the stretch, and then apply the stretch to it. So first of all, we need to go to the left 5, left 5, and down 3. The origin is going to be where this graph starts. Make sure you remember your key points, your key input values for the square root function. That would be 0, 1, 2, 3, 4, 9. Let's see, the next one after now would be 16, 10, 11, 12, 13, 14. That's too far off. I'm not going to worry about it. If I didn't have the 3 there, and I were just doing a normal square root function, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So you would have a shape that would look like that. That's your square root shape that is shifted to the left 5, and down 3. Let's put it all together for us, though. We'd have to apply the stretch of 3, which means 0 times 3 is 0. The square root of 1 is 1, now times 3. So 1 times 3 is 3. So 1, 2, 3, like that. The square root of 4 is 2, and then 2 times the scalar factor here of 3, so 2 times 3 is 6. So we're going to go up 6 units from this baseline. So make sure you understood what happened there. We did the square root of 4 to get 2, and 2 times 3 is 6. So we measure that 6 from that new horizontal x-axis, what we have here in that teal color. The square root of 9 is 3. 3 times 3 is 9, so it's going to be 3, 6, and 9. And so you see that when we connect these dots, we are still going to have that square root shape, only we took that square root shape and we just stretched it out like that. Now, as almost like a follow-up to this, imagine if I asked you to do this. If I said f of x is equal to 2 times the square root of x plus 5 minus 3. The only difference between what we have here in red for f and in black for g is the lead coefficient here of 2 in terms of how it stretches things. So this is when you just have a 1 in front. This is a 3. And so I hope it makes sense that if you have a 2, it should be somewhere in between. Right? So the square root of 1 is 1 times 2 is 2. Square root of 4 is 2. 2 times 2 is 4. Yeah. The square root of 9 is 3, and 3 times 2 is 6. And so this is what it would look like if it had a lead coefficient of 2. So there's 1, 2 stretches it, 3 stretches it even more. But notice that they all still have that same origin point there that is -5, -3. And the thing I like about these graphing techniques is that we don't have to create a new t-table of values. We take what we already know, and we just now graph those points from a new point of origin. And I just kind of ignore those original x and y axes. At least that's the way I like to do it. If it's a multiple choice test, it's really easy to pick it out. And if you graph by hand, just have to know those key points, and you're going to be okay. All right, now to some of the tough ones. Let's do f of x is equal to -1/2 x to the third plus 2. And let's make sure that we understand all that's going on here before we start graphing. The key function, the key shape that we have is determined by x to the third. So we just talked about those at the beginning. We said that x to the third is the cactus shape. All right, got that much down. What about the stuff that's in front? The negative here means that we're going to be upside down. So it's going to take the cactus shape that we have, and it's going to flip it upside down. That's all that it means. So it means whenever you plot those key points, you're not kind of doing it turned upside down. This 1/2, the 1/2 is going to give us a compression. And the reason this gives us a compression is because it's a factor of 1/2. So it's something that's less than 1, so it's going to be taking our cactus and scrunching it up a little bit. And then finally we've got the +2. So that is outside, that's completely disconnected from the cube. The cube doesn't touch it at all, and you're going to go up 2 units. So for us, that means we're going up 2, but I'm not going left or right at all. So if you want to dash out that y-axis, you can. All right, so let's think about what these key points are, what the key points do for the cubing function. So 0, 1, and 2. All right, so 1 cubed is 1, but since we have the negative, we're going to be upside down. Now, this is just going to be before I do the 1/2, because I want to do these points first, so that when I do the 1/2, it makes a lot more sense. So 1 cubed is 1, but it's going to be upside down. 2 cubed is 8, and so that's going to be down here. For the cubing function, it has point symmetry, just like the cube root function did. So when I go to the left one, I'm going to actually be up 1. If I go left 2, 2 cubed is 8. And it will look something like that. But we have the 1/2. We have a compression. And what that compression does is that it takes these changes right here. This was a change of 1, and it's going to cut that in half. From here to here is 8. But now we're going to do 1/2 of that. So that's going to be down 4. And the same thing is going to happen on the left side. This is going to be half of 1, which is a half. Half of 8 is 1, 2, 3, 4, like that. So we're kind of flat right here in the middle. And then we're going to curve. We're going to curve down. Now, I'm not going to lie to you. Even with the 1/2 in front of the cubing function, that's still pretty steep. It's kind of hard to see how that really deviates from the original. So the original would have looked like this. And it's really hard to see how different it is. But you can barely see it over here where it's getting really, really steep. This guy is still getting steep, but he is just growing at half that rate. Okay? Really, these are not the easiest ones to do when you have a coefficient in front. The best ones are when you have absolute value. So if I do the f of x equals negative 5/3 times the absolute value of x plus 2 plus 8. So the absolute value symbols right there tell you that we have a V shape. And let's look at the rest of this. The negative tells me that I'm going to take that V shape and I'm going to turn it upside down. The 5/3, believe it or not, is going to give me a vertical stretch by that factor of 5/3. You might be saying, why is it a stretch? It's a fraction. It is a fraction, but it's an improper fraction, which means its value is greater than or equal to 1. So since the numerator is bigger, it actually has a value greater than 1, so we're going to take that V shape and we're going to stretch it. Well, I guess actually, we're going to take this V shape, negative turns it upside down, and then the 5/3 is going to stretch it. Okay? Now let's figure out how we've shifted up, down, left, and right. Inside I see a plus 2. So that means I'm going to go opposite of that. I'm going to go to the left 2. And the plus 8, I'm going to do exactly what I see. And I'm going to go up 8 units. Alright. So I'm shifting to the left 2. So let me put my new and improved y-axis there. I'm going up 8. So I have that. The intersection will be your vertex. Now you're going to see that whenever I graph an absolute value function, I'm not marking off 0, 1, 2, 3 and all that stuff. And the reason I don't need to do that is because, as we've mentioned, with absolute values, they are made up of linear pieces. And since they are linear, we can just treat them like lines, find the slope, and use the slope to get extra points. So using this negative 5/3 in front, from here, you're going to go down 5, 1, 2, 3 to the right, and 1, 2, 3 to the left. And do it again. Go down 5 and over 3. From here, go down 5, over 3. And you keep on going until you run out of room and you can't fit any more points on there. So I hope that you guys can see that we took this absolute value, turned it upside down, stretched it a little bit, then we slid it to the left 2, up 8. And then we finish this just by connecting the dots. And we can use a straight edge, as I've mentioned, because of the way the absolute value is made up of linear pieces. So there we go. Doesn't that look beautiful? All right, let me do a couple more examples to wrap this up. Suppose we say that f of x is equal to 1/4 x minus 4 quantity squared. And let's think about what this is going to look like. All right. First of all, we see the square, so we know that we are dealing with a parabola. All right. What do we know about that parabola? I see the 1/4 in front. The 1/4 is a fraction less than 1, so that means that we are going to have a compression. And with this compression of 1/4, that means that the graph that you're used to seeing for that parabola, okay, is not going to be growing like this. He's going to be growing at 1/4 that rate. So whatever output values you're used to getting, you're going to be dividing it by 4, which is really going to hamper how he grows. And then we have the -4 on the inside, so I see -4 inside, but it's a horizontal shift opposite of what I see. So we're going to go to the right 4 units. All right, so going to the right 4 units is going to look like this. You didn't move up or down, so we're going to keep that guy right there. And I'm going to start right there at that guy. Now, I want you to maybe this is one of those times where you make a little chart just so you can see what things are going to be. So here's x with some of those key points that we have where we end up with x squared, right? So 0, 1, 2, 3, 4, and so on. So 0 squared is 0, 1 squared is 1, 2 squared is 4, then we get 9, and 16. So that would be the normal points that we would graph relative to this. However, we have the 1/4, right? So when I do 1/4, I'm going to do this in red so you can see that a little bit better. When I do 1/4 x squared, the order of operations is, we'll say you square first and then you divide by 4. So that means I'm doing 1/4 times 0 and I would get 0. 1/4 of 1, I get 1/4. 1/4 of 4, that gives me 4 over 4, which is just equal to 1. Right? And we do the same thing here. Really, you're just taking these guys and you're going to divide them by 4. So 9 over 4 as a mixed number so that we can graph it very well is going to be 2 1/4. This is 16 over 4, which gives me 4. So you see we're taking all of those outputs and we're now dividing them by 4. So when I graph this, there's 0, 0. When I get over here to my 1, I get 1/4, so that's something like that. When I go over here 2 units out, 2 squared should have been 4, then I divide by 4 and I get 1. And then I'm here at 3. 3 units away from that new origin. 3 squared is 9. 9 divided by 4 is 2 1/4, so 2 1/4 like that. And then at 4. 4 squared is 16, and then I divide that output by 4, and I get 4. We can actually go one step more here, because 5 squared gives me 25, And I can do 25 divided by 4 to get 6 1/4. So that means that my next nice point that I have, I get 5, and so it's going to be 4, 5, 6 1/4 like that. And then I can take those points and copy those on the other side of the graph. So there's 1/4, 1, 2 1/4, 4, 6 1/4. And if you go one more, you think about this. So this is 5, 6 squared is 36, and 36 divided by 4 is 9. So that's the last nice point that we get. And then we connect the dots. Just like this. Now, if I did not have those, if I didn't have the 1/4, okay, then this would have been growing at a much steeper rate. So you would have had 1 squared is 1, 2 squared is 4, 3 squared is 9. And when you plot this parabola without the 1/4 compressing it, there's what you would have. Now again, what you need to understand is that when I have the 1/4 there, it's a vertical compression. So you're taking this guy that was right here and you're putting the press on it. And when you press this down, he can't grow as fast. And so that's why it looks like it's a little bit wider. But again, you need to think about how you are taking this point right here and you divide it by 4 to get here. 9 divided by 4 gives you 2 1/4. So you are compressing that guy down. Yeah. So that's a lot of fun, right? Well, I think that's a good place to end it. So thank you guys, anybody who has been lurking, anybody who has been joining the streams for this review of the first half of our semester of college algebra. So, hope you guys learned something. Hope you found this useful. I will be adding more videos, new videos, updated videos to my YouTube channel. So, please make sure that you go and you check that out. Right there, there's all the information. And yes, Kevin, thank you so much for stopping by.